In any graph of data, we want to find out as much information about the various features of the data as possible. This information will be important when choosing what kind of procedures will be appropriate to use. We use the following saying to help us thoroughly analyze a graph of data. We call this saying Cisco. The first S stands for shape, or the overall pattern. Then we have center, the spread, clusters, and outliers. As you can see below, we have several different graphs. All of these graphs in each column share the same shape. The first shape that we want to discuss is normal. Another name for that would be symmetric. As implied, a normal graph has a symmetric shape like this, where if you folded it right down the middle, it would line approximately on top of each other. You can see that the dot plot also has a similar shape. The box plot, you can see, is about evenly distributed in each quartile. So each section of our box plot is about even. And then for our stem plot, when we turn it over to the side like this, you can see that it's also normally distributed. Real life examples of a normal distribution would be women's heights. The reason being that you would expect most women to be in the same height range in the middle, and then you have some women that are on the very small end and then the very tall end. Another example would be a fair test, where most of the students score in the middle range, some doing really well and some doing very poorly. Our next shape is called skewed right. Another name you may hear is positive skew. The direction of the skew has nothing to do with where the majority of the data is, and on contrary, it's where the non-majority is. So if you look at this graph right here, the majority is on the left side, but the name is skewed right. So we're actually looking at the tail. Since the tail is on the right, that is called skewed right. The least amount of data is on the positive end of the number line. You can see the same form for over here. In our box plot, notice that the majority of our data is on the left side, with the outliers pulling the rest towards the right. And then finally we have our stem and leaf plot, which you see the majority of data is on the left, and then skewed right, so the tail here is on our right side. Other examples of skewed right data are a number of siblings that people have. If you ask your classmates the number of siblings they had, probably somewhere around 0, 1, 2, 3, and then getting smaller and smaller and smaller as the number line increases. Another example for this would be a hard test. With a hard test, you would expect most of the scores to be on the lower end, where only a few people do well on the right end. That leads us to our last shape that we're going to look at, which is skewed left. And as you can probably guess, this is a negative skew. So much to the opposite, since the data is being pulled towards the left side, the tail is on the left, this is skewed left. Same can be said about our dot plot. It's getting pulled towards the left side. Our box and whisker plot, majority of data is on the right, with our left side being pulled out this way by the outliers. And then once again, we've got our stem plot looking like this, with our tail on the left. Other examples of a skewed left graph would be life expectancy, so how old people tend to live until. In this country, people tend to live till they're older, so you have many of the ages being towards the right end of the number line and very fewer being on the left or the smaller end of the number line. Another example would be an easy test. You'd expect most scores to be really, really high, with only a few people faring poorly. So that takes care of our shape. Next we want to talk about the center. For the following graphs, you will use the median as your measurement of center. For continuous data, we're going to use the interval in which the median is located. Since we can't identify every single data point, we can only figure out where the median would be. If the data is discrete, then the center is going to be the value instead of the interval. For the following graphs, our spread is going to be the range. Cluster appear if there are gaps in the graph. If there are gaps, then the clusters are the bins grouped together on either side. And finally, we have our outliers. In a histogram, especially if the data is continuous, we cannot use the formula to figure out what each individual data point is. So instead, we're going to eyeball whether or not we believe there to be an outlier, something that's significantly different from the rest of the data. So for example, you can see in histogram A that this is going to be discrete data. And the reason we know this is because the graph on the x-axis is giving us midpoints. So first let's talk about the shape. If we had to say that this was a shape, you could argue a couple things. You could say that the shape is symmetric. You can see that the majority of data is right here in the middle with only a few on this side and a few on this side. It is a little bit difficult to tell, mostly because we have such few data points. Therefore, you could say symmetric, or since it's not that obvious, we could say that it is indistinct. Next, we want to find the center. So we know in a histogram, each bar represents the frequency. So there is 122, 2 24s, 4 26s, 3, 6, 4, and 1. If we add up all these data points, 1, 2, that's 3, 7, 10, 20, 21, there are 21 data points. That means that the median is going to be the 11th data point. So going back to our histogram, there's 1 here, 2, so there's 3 data points here altogether, then 7, then 10, then the 11th data point would have to fall in this bin right here. And since this is discrete, we know that the center must be 30. Our spread is the range, 34 to 22, so our spread in this case is 12. Are there any clusters or gaps? No, there are not. We have no gaps in this graph, therefore there are no clusters. And as you can see, all the data is pretty close together, therefore there are no variables. I'd like you to continue looking at each histogram and identifying its Cisco, and conclude the rest of the questions on the back page. Good luck!